Guys, and let's see how you solve this to accelerate this process, right? I already make a drawing here. I made a sketch of this problem. So the problem, we have two plates, infinite plates are here. I put like this, right? But it would be more appropriate if I graphically represent this like this, right? Like a wavy. I didn't put, so I don't add sketch. So I didn't put, but those are infinite plates, and they're positioned at minus 50 centimeters and plus 50 centimeters, and they have different charge densities. One has minus 50 nanocoulomb per square meters, and the other one has 25. So okay, all the information here. It's very important to make, guys, like a sketch. I make a sketch here, so this is a 3D representation of this problem, and here I made one 2D, because then I can actually recognize how to apply the principle of superposition here to solve this problem, right? We have the first plate here. I'm considering like infinite plate, and this is a negative charge distribution, right? That's negative. That means that the field is convergent, and I'm calling this field like a E1. And for the other plate, that is actually divergent field, to generate a divergent electric field, I'm calling Q. As you can see, right, in the region between the two plates here, I put in different colors. The region between the two plates, these two, the two electric fields, they added up, and in the region to the left, this plate here, we are going to subtract. So with this in mind, back, we have to remember here that the electric field for an infinite plane is given by this expression here. If you don't remember, you can go back to our previous class here. This one. Okay. We derived the expression for infinite plane, right? In our second lecture, the, the expression. Let's go back to our class today. Okay, you have this, and let's see what you have inside the planes. Very big. By the vectors here. Put in colors. Let's put lines here. Colors. Easy to recognize. Nice. I'm going to represent this electric field E1. So this is going to be according to my reference frame here. Electric field is going to be minus the magnitude of the field, in the negative I hat direction. Okay, you have this, and the other field representing the other field is going to be E2 using the same direction. It's going to be E2 in the minus I hat direction. So we can write this electric field inside using the principle of superposition, right? You have to sum up them. We can write this minus 1, 2, I net direction, and we can use the expression for the infinite plane. It's going to give me epsilon 0, epsilon space density. This is in the, just me check if I didn't make any mistake. Okay, okay, right. Okay, and let's analyze our electric field outside the plates. But I'm not interested for every single point. I'm just interested in points around this region here for for axis greater than 0.5 meters, right? So I'm interested right here, the right side of the positive plate. Okay, let's go there. Again, let's write the, as a reminder, right? Let's write the electric field for outside the plates in that position right there. I'm going to have the E1 going to be, again, it's going to be in the negative direction, so it's going to be E1 I hat. Don't forget, this is a vector. Y is facing. Let's see in the other direction. And the other vector is going to be, drawing here, going to be in the positive direction, so this is going to be E2 J. No, sorry, I hat positive.
Professor, I have a question here.
Yes.
Um, for the electric field from the plates, you wrote that the equation is sigma by 2 eta naught. Like for each plate, shouldn't it be sigma by eta?
Sigma. This one you're saying that is like this?
Yeah, and then when we add, like, then it will be sigma 1 plus sigma 2 by eta naught.
When you sum up, you say you are talking about this factor here, right?
Mm-hmm.
Yeah, I made a mistake. I can check later, but let me just go back here. Back to the electric field here. Okay, the electric field it is, okay, sigma over 2 twice epsilon 0, right? Okay, so okay.
For
Maybe
one plate, it should be sigma by eta, I guess.
for this plate, you mean? For one plate.
Yeah.
Ah, I see what you mean. Yeah, maybe I made a mistake there. Or maybe I made a mistake in the factor. Okay, you're going, guys. You can review later. Okay, maybe I know what you said. Maybe a mistake here with this factor, because this is for one plate, and but I'm considering every plate individually. Okay, the way I solved, I forgot, for example, the one plate, and I'm considering the effect of only one plate alone, and then I'm considering the other one. So this is kind of not kind. It is the superposition principle. So I think this is correct. I'm not sure, but you can check later and we can discuss. Okay? But I think, okay, open to discussion. Shall I proceed? The factor is not so relevant here, so is the most important part is actually uh, is to apply the principle of superposition, right? I mean, considering one plate first, for example, the negative plate, tan, 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 and then you consider the positive plate later, and then you like superpose the effects. This is the most important part here, and I okay. But thanks for the
I'm sorry. I think you are right.
okay, no
Uh,
problem. Okay, I can check
uh,
later, and then I let you know. Okay, is it fine?
yeah. Yeah. Okay. Okay.
Okay, let's go and then write the electric field for the inside for the outside plate. For the outside of those plates. So this is going to be superposition of these two is going to be here, right, guys? This side. So here is going to be one minus the other. So this is going to give me one epsilon 0. Let's just write like that one. It's going to be a minus 1 plus in the I head direction. A if we substitute here is going to give us the difference to charge density, the I direction. Okay. Yeah, this is going to give some number. I don't know. Have to substitute those values there. But what it wants to know is actually the uniform field inside the potential difference inside. For a uniform field, you know that this is going to be the proportional to the electric field and the distance, right? We found this last class. So we can actually now superpose all this, right? You can superpose this part here for the inside, this one from the outside. So you are going to have here the electrical field side, that the distance, right? Plus this one. Oh, put some 5 this, yeah, here, right? Okay, and then if you substitute all these guys, we're going to find, we can factor here, and we can draw. Part two, and uh, guys, if I found, you can check please, and we can discuss this next class. I found 2.4 times 10 to 3 volts. But I'm going to put here to revise, babe. Okay, what is, we can discuss next class. So it's about this, right? Okay, and let's go to the next example. Good. Last one for the potential is this problem. So this is very common, very common type of problem. 1 minute.